Good morning to one and all. In today's lecture, we'll discuss about the generation of PAM signal. So PAM is your pulse amplitude modulation. In the pulse amplitude modulation, the amplitude of the rectangular spaced pulses are varied in proportion to the corresponding sample values of a continuous message signal. So basically, your pulse amplitude modulation use a process that is similar to your flat top sampling. So here we can see in the figure, it is given here, this is your GT, that is your PM signal, this is your message signal. These dotted line represents your message signal MT having a pulse width of T. So this is your flat sampling. Now coming on to the generation of PM. For the generation of PM, it involves two operations, that is sample and hold. So first is your instantaneous sampling and second is the lengthening the duration of each sample. In instantaneous sampling of the message signal, here the message signal is at every TS second. So we can say that the sampling rate is equals to Fs is equals to 1 upon Ts according to the sampling theory. Now second is the lengthening the duration of each sample. So to occupy some finite value T, we used lengthening, and to avoid the use of excessive channel bandwidth, we have bandwidth is inversely proportional to 1 upon T, where T is your pulse duration. So we can say if the channel bandwidth increases, then your T decreases. Clear? The pulse duration will decrease. Now for the analysis of PM signal, we use sample and hold filter. So mathematically, your PM signal is expressed as GT is equals to summation M NTS into HT minus NTS, where TS is your sampling period and NTS is your sample value of MT at T is equals to NTS. Here, the HT is the standard rectangular pulse of unit amplitude and duration T. So the PM signal is obtained basically from the ideal sampling, where your M del T is equals to M NTS into ST, where your NTS is the baseband signal and ST is your unit impulse train. Here we can say that we have MT and ST and T is equals to NTS. So for ST, we have ST is equals to summation n equals to minus infinity to infinity del T minus NTS, where del T minus NTS is a time shifted delta function. And at T is equals to NTS, M del T, since we know the value of ST is equals to summation n equals to minus infinity to infinity del T minus NTS. So we can put over here. So your M del T is equals to summation n equals to minus infinity to infinity M NTS into del T minus NTS. So basically for the generation of PM signal, some modifications is performed. So in the modification, we take standard rectangular pulse. So basically we took the standard rectangular pulse. So we use the convolution of M del T and HT. So after modulation, we will get M del T convolution of HT, then only we get a PAM signal. So we can say your M del T convolution of HT is equals to integrate minus infinity to infinity M del tau HT minus tau d tau. Using the property xt convolution yt is equals to integrate minus infinity to infinity x tau into y t minus tau d tau. Now we know that M del T is equals to summation n equals to minus infinity to infinity M NTS into del T minus NTS. So in place of M del T, we can put this. So it will be equals to integrate minus infinity to infinity summation n equals to minus infinity to infinity M NTS into del tau minus NTS into HT minus tau d tau. Now taking the MNTS constant outside, so we'll get summation n equals to minus infinity to infinity M NTS integrate minus infinity to infinity del tau minus nts into t minus tau d tau. Now here we will be using the shifting property of the delta function. Now coming on to the shifting property of delta function. Now this is the property of shifting property of delta function. Here we can say that your integration minus infinity to infinity del tau ht minus tau d tau is equals to del t convolution of ht. So here if we do the convolution with the delta function, we'll get the same function. So that is equals to ht. Now here we can say we have the shifted version, that is your del tau minus nts. So for that we'll use the formula, that is your integrate minus infinity to infinity del tau minus nts into ht minus tau d tau is equals to del t minus nts convolution of ht, that is equals to ht minus nts. So we'll put ht minus nts in place of del tau minus nts. So we get that is equals to summation n equals to minus infinity to infinity. M and ts was outside the bracket only. So here we got ht minus nts. So we can say that your m del tau convolution ht is equals to gt, that is your gt is equals to summation n is equals to minus infinity to infinity m nts into ht minus nts. So this was all about the generation. In the next topic, in the next lecture, we'll discuss about the demodulation. Thank you.